In this session and the next few sessions, we will talk about calculations involving chemical formulas. So we'll discuss formula masses, percent compositions, and the very important concept of a mole, which is extremely important whenever we deal with chemistry related calculations, which will be what we'll be doing for the rest of the chapters that in this course. So the whole idea of moles and molar mass and Avogadro's number and all will be discussed in the next few sessions of this chapter. Okay, so let's get started with formula mass. If you remember correctly, a few sessions ago we talked about something called an atomic mass. And if I were to ask you what is an atomic mass, a very simple answer to that question would be it's the mass of an atom. Similarly, what is formula mass? Formula mass is the mass of a formula unit, a unit that is described by the chemical formula of a substance. The total mass of that unit is called the formula mass. Now, just as the atomic masses of elements that are given in the periodic table are relative masses, if you remember correctly, they are all relative to a single atom, to the mass of a single atom of carbon-12 isotope. Similarly, formula masses are also relative to the same standard. These are not absolute masses, they are comparative, relative to that of a single atom of C12 isotope. Formula masses are also expressed in units of atomic mass units, AMU, and these are calculated by adding up the atomic masses of all the atoms present in the formula unit. So all we do is we add up the individual atomic masses of every single atom in one formula unit of the substance, whatever that substance is. Now, please do remember that when you are doing this, when you are adding up the atomic masses of elements in order to calculate the formula mass of a formula unit, then we did decide to round all the atomic masses to 2 decimal places before we actually figure out the formula mass. Now, this is a guideline we are setting for our class just so that we can all be consistent in our answers. It is not a rule by any means. Okay, so let's try it out. Let's go ahead and calculate the formula masses for some compounds that are listed here. I will do a couple, walk through the process of a couple of them, and then you can do the rest. For example, H2O, that's the formula unit, 1 molecule of water. So as we said before, we add up the atomic masses of every atom in that formula. So in this case, there are 2 hydrogen atoms, and the atomic mass of each hydrogen atom is 1.01 AMU, rounded to 2 decimal places. And there is also 1 oxygen atom, and the atomic mass of 1 oxygen atom rounded to 2 decimal places is 16.00 AMU. When you add these together, the formula mass of H2O is 18.02 AMU. Please remember that if all the atomic masses are going to be in 2 decimal places, the formula mass must also be in 2 decimal places because we are adding the individual atomic masses. Okay, let's do one more. How about C9H8O4? So there are 9 carbon atoms. Each carbon atom has a mass of 12.01 AMU, 8 hydrogen atoms, and each hydrogen is 1.01 AMU, and then 4 oxygen atoms, and the mass of each oxygen atom is 16.00 AMU. If you calculate this, it comes out to 180.17 AMU. Please go ahead and pause the recording while you calculate the formula masses of the remaining 3 compounds. So the formula mass of sodium chloride comes out to be 58.44 AMU. Nitric acid, HNO3, 63.02 AMU, and Sucrose C12H22O11, that's the common sugar that we all eat in almost everything, is 342.34 AMU. Please do remember, and I will highlight this information, that these are relative masses relative to carbon-12, and these are in units of AMU, and they are simply calculated by adding the atomic masses of every element, every atom, rounded to 2 decimal places. Okay, so next topic is percent composition of a compound, which is basically defined as percent by mass of each element in the compound. So what percent of the mass of each element is there in the compound is called the percent composition of that compound. It is calculated simply by, as you would calculate any percent, this is calculated by dividing the mass of the element by the mass of the compound times 100. Now this formula you must remember. You must know this formula at all times. So percent composition is defined as the mass of element of in the compound divided by the total mass of the compound times 100. So for example, if we had to calculate the percent composition of ammonia, the first thing we need to know is what is the total mass of the compound. In other words, what's the total mass of this formula unit, which as in previous slide we said is formula mass. So let's go ahead and calculate the formula mass. That would be 14.01 AMU for nitrogen plus 3 times 1.01 AMU for hydrogen, which together gives us 17.04 AMU. That's the formula mass for ammonia, NH3. So now all we have to do is calculate percent mass of nitrogen in that, and then percent hydrogen by mass in that compound. Percent nitrogen will be mass of nitrogen, 14.01 AMU, because there is only one nitrogen atom in one molecule of NH3, divided by the total mass of the compound, that is 17.04 AMU times 100. When you calculate this, we get 82.22% of nitrogen, percent nitrogen. Now when it is time to calculate percent hydrogen, yes, we can do 3 times 1.01 mass of hydrogen, total mass of hydrogen in one molecule of ammonia, divided by the mass of the molecule of ammonia times 100. We can definitely do that. Or we can also, since there are only 2 elements and the total percent of anything has to be 100%, we could also just do 100 minus 82.22. Percent total has to be 100%. So either way you solve it, you should get the same answer, and the percent hydrogen comes out to be 17.78%. Okay. Let's look at another problem using the percent composition of a compound concept. So the question is asking us to calculate the percent composition of the compound with the given information. So let's evaluate the information that is given in this case. We know that a total of 49.31 grams of the sample is decomposed. That is the mass of the compound. And upon decomposition, decomposition means that the substance is breaking down into its elements. It leads to so many grams of nitrogen, so many grams of sulfur, and that of oxygen. So we basically need to calculate percent nitrogen, percent sodium, percent sulfur, and percent oxygen by mass. So go ahead, please pause the recording at this stage while you calculate, and then we'll check our answers. So percent sodium comes out to be 15.96 grams divided by 49.31 grams times 100, which after rounding to 4 significant figures comes out to be, and then sulfur comes out to be 11.13 grams divided by 31 grams times 100 equals 22.57%, rounded to 4 significant figures because the masses are all measurements. Percent oxygen, 22.22 grams of oxygen in 49.31 grams of the compound times 100, which comes out to be 45.06%. Rounded again to 4 significant figures, keeping in mind the rules for significant figures that we discussed very early on in this course. One final check that I would ask you to always make when you're dealing with percent composition problems is to add up the individual percent compositions and make sure that the total comes out to be 100%, not 100.01, not 99.99. It needs to be 100. In fact, in this case, it would need to be 100.00 because all our percents are in 2 decimal places. So the sum of that needs to also be in 2 decimal places. If that does not happen to be the case, so then you will have to go back to the percents that you calculate and use your judgment in terms of re-rounding one of them to in such a way that the total does come out to be 100%. You cannot have less than or more than 100% of something total. Okay. Here's another question for us to attempt. Feel free to pause the recording at this time while you read the problem and try to solve it on your own. So the question is once again asking us to calculate percent composition of 10 grams of a compound that is created with the combination of 3.34 grams of sulfur and 10 grams of oxygen was used, but was all the oxygen used to make the compound? No. Of the 10.00 grams of the oxygen used, only 3.34 grams of oxygen was left unreacted, meaning this amount of oxygen did not become part of the compound. So you have to be very careful and read the question carefully in order to decide the numbers, the masses of each of the elements. So calculating percent sulfur is not difficult because we know 3.34 grams of sulfur was used to make 10.00 grams of the compound. So that gives us 33.4% sulfur. But we do have to think about oxygen. How do we use oxygen? Percent oxygen, we need the mass of oxygen. Did we use 10 grams of oxygen to make the product? No. Did we use 3.34 grams of oxygen to make the product? No. In fact, the amount of oxygen that actually went in the product is 10.00 minus 3.34 grams. It's a difference. It's the actual oxygen that reacted to make the product, whose mass, of course, is 10 grams of the compound times 100. So when you solve this, the percent oxygen comes out to be 66.6% oxygen, and the total of this is 100.00%. Okay, so here's a question where they're asking you to confirm that the given percent composition matches a certain compound. In this case, the certain compound is carbon disulfide. Now, the basis of this question is the simple idea that we discussed several sessions ago, that a compound must have a definite and constant proportion by mass. In other words, for a compound to be a compound, the percent composition must be the same for that compound. If the percent composition is not the same as what you would expect, then it's not that compound, it's something else. So the compound that we are dealing with in this question is carbon disulfide. The first thing that you have to solve is, what is the expected percent composition of carbon disulfide? So let's do that. In order for you to figure out the expected percent composition of carbon disulfide, we have to answer the question, what is the chemical formula for carbon disulfide? If you go back to the sessions in the previous chapter that we've already attempted, you should be able to tell me what is the chemical formula for carbon disulfide. Exactly, carbon disulfide is CS2. It's a molecular, non-acidic molecular compound. So what is the total mass of this compound? Meaning, what is the formula mass of carbon disulfide? If you calculate the formula mass of carbon disulfide, it comes out to be 76.13 AMU by adding up the atomic masses of every atom rounded to 2 decimal places. Once you have that figured out, you can calculate percent carbon, knowing that there's only one atom of carbon, divided by the total mass, gives us 15.78%. Please remember that you're rounding in this case to 4 significant figures because your measurements are in 4 significant figures. And then of course percent sulfur will be 2 times the mass of one sulfur atom, which is 32.06 AMU, rounded to 2 decimal places. Total mass is 76.13 AMU times 100. I forgot that was also times 100, equals 84.22%. So these are the expected percent composition values for the compound CS2. The observed percent composition values that were given in the question was 15.77% carbon. That's pretty close to what we calculated, and 84.23% sulfur, which is also very, very close, within rounding error of the ones that we calculated. So from here you can conclude that yes, the given percent composition values do match the calculated percent composition values for the formula CS2.